the first part of that of the algorithm is it says the last element of the array is going to be the pivot. Okay, so our pivot value is going to be 4. Okay, and its position is high, which can be taken as the last element in the array. Okay, and then that means this is kind of, we don't really care about this element as we're iterating through it. There's kind of, we imagine a kind of a basic wall there. Okay, so our pivot is going to be our array, whatever the high position of that array is. Yeah, high. Okay, so that's how we get the value in our pivots. Then we have these two other pointers. We have I and we have j. Okay, and they have different roles. Okay, so I is going to be whatever the low value. So on the first time around, low is just going to be 0, or the first element in the array. So we're going to have low minus 1. Okay, so what that means is I is going to start its life in this partition algorithm pointing outside the array in the -1 position, which is, as we know, an illegal position. Okay, and then j will start off pointing at the low position. Okay, so our second pointer j is going to point here. Now, these are our two main pointers that we need to keep track of. Okay, and their jobs throughout this is going to be, so for I, it's going to tell us where the small numbers are stored. Okay, so it's going to tell us where the small numbers are, and then j is going to tell us the next number to compare. Okay, so right now we can see how this works. Okay, at the very beginning we haven't found any small numbers, so it kind of makes sense. We haven't found any small numbers yet compared to the pivot, which is 4. Now we can glance across this array and see, well, I can see 2, 1, and 3 are all smaller numbers than 4, so I know they exist, but we haven't found them yet. Okay. And then j is going to be essentially the next number to look at. Okay, so the next number at the start of this algorithm is the first number, if that makes sense. So what's going to happen is we're going to have this, I can draw it, I guess. Here is where it starts off. We're going to arrange our small numbers on this side and our larger numbers on this side. Okay, and this is going to move, this kind of imaginary line is going to move throughout this algorithm. Okay, but for now, this is our setup. Okay, we have our low -1, which is pointing out here, and our j pointer pointing to the first element. And what we're imagining is we have this, all these numbers over here to explore and to compare with the pivots. Okay. So that's the first part, okay, before we even start our for loop. Okay, so I'm going to go through each iteration of the for loop. Okay, so the question we'll ask every time is where we're currently looking at, the current number or the next number, as I called it, is it less than or equal to the pivot? Okay, we're trying to find it. Is it smaller than the pivot? And we remember our pivot is over here. Okay, so we're always comparing against 4. That doesn't change. Okay. If this is smaller, okay, then we want to swap, and we want to swap. I can't remember what it was. Was it a of I with a of j? Okay, we want to swap those two numbers. Okay, so in the very first iteration, okay, we're going to ask, is aj less than the pivot? Okay, so j is currently pointing here, okay, and I is pointing here at -1. Okay, so we're going to ask, is 2 less than the pivot? Yes, it is. Okay. If this is less than the pivot, then we need to swap. But remember from the algorithm, and I should have this on screen, we increment I if the current number is less than the pivot. Okay, so we go from it starting off as -1 to becoming 0. Okay, so kind of weirdly in this, the first step's always a little bit weird when you have these minus indices, but we're swapping, these both have the value of 0 at that point in time. So this, in this first iteration, moves to also point at 2. Okay, so we do a swap. And because it's swapping 0, 0, it doesn't move anywhere, but we actually swap this number. And now I is pointing at 0. And what we imagine is this wall between the small numbers and the large has moved forward. Okay. Remember here, I said it kind of starts off outside the array and it's going to move across. Okay. So now we know where the small numbers are. I is going to keep telling us, okay, this is where the small numbers should be. Okay. And then because the for loop keeps incrementing j each time, at the end of this, then j is pointing to 8, so it moves forward. So j will always advance by 1 in this for loop. I will only advance if we actually perform a swap. Okay, so that completes the first iteration. We've moved I forward. And we're going to keep doing the same thing. We're going to ask, is a of j less than the pivot? So the state of my array, I'll keep updating it. 7, 1, 3, 5, 6, and 4. Our pivot is here. And in this case, we're now considering 8. Okay, so I is pointing to 0 and j has moved to 8. Okay, and it's pointing there. Is 8 less than 4? No, it's not. Okay, so in this case, there is no swap to carry out. Okay, so because there's no swap to carry out, our I pointer doesn't advance, but at the end of that for loop, we add 1 on to j, so it moves. Okay, and then we get this idea that, okay, these are all the numbers, the kind of unexplored numbers. Okay, but this for loop is going to drive j along, so we visit each of them. Okay, so then we move on to the third iteration, and 2, 8, 7, 1, 3, 5, 6, and 4. Our partition. Okay, at this point in time, we again have no swap, okay, because we're looking now at j has moved on to point at 7. 7 is not less than 4, so we're going to move on again. Okay, so again, this time, no swap for those numbers. Okay, so far, not incredibly exciting. I should just make sure that I is still pointing here. Okay. Let me keep this here so I can remind myself. That was one of those mistakes. Okay, so the fourth iteration. Okay, so we have 2, 8, 7, 1, 3, 5, 6, 4. Okay. What's going to happen this time? So we're now j is pointing at 1, and 1 is less than 4. Okay, so we're going to need to perform a swap. So there will be a swap this time. Okay, so a couple of things are going to happen. Because there's a swap, we then increment I. Okay, so I is going to now going to point at position 1. Okay, remember we were at 0 for a while, we're now at 1. Okay, and what this has done is it creates, now these are all the small numbers, and j is currently pointing at 1. Okay, we've compared 1 to 4, which is our pivot. Now we have to swap. Okay, remember we swap whatever as I is pointing to with whatever J is pointing to. Okay, so now what we do is we take the 1 is going to be here, and the 8 is going to end up over here. I can, yeah. Oops. And 8 is going to be here. Okay. So now we've moved the small numbers along, and we can sort of see that we've actually, this is kind of working because we have our small numbers in this little collection, and we're keeping our larger numbers that we've seen so far here by keeping it. We've swapped the 8 to keep it in the right place, and we still have these remaining numbers unexplored. And at the end of this iteration, of course, J always advances to the next. So we'll then look at 3 next. Okay, so then in our 5th iteration, so we now have 2, 1, 7, 8, 3, 5, 6, 4. This is our pivot. J is currently pointing at 3. I has moved here. So we make the question, is J less than the pivot? What it's pointing at, 3 is less than 4. Okay, so we have another swap. Once we have a swap, we then have to increment I. Okay, so then what we see is this actually moves along, and it's pointing at 7. Okay, so now we have to swap 3 with 7. Okay, so actually the 3 will jump to here, and the 7 will jump to here. At this point in time, it's kind of interesting because you can see the 8 and the 7 are actually flipping place, which is can be seen as kind of inefficient, that it's not very stable, that we're actually, things that we've already sorted, 7 and 8, we unsorted them in this particular move. But again, we kind of tolerate that for the way this particular algorithm works. Okay, let's keep moving. Okay, so J at the end of that will point to 5. There's the next element, and I is currently pointing there. Okay, so 6th time around, we now have 2, 1, 3, 8, 7, 5, 6, and 4. We have our pivot, where J has moved to point to 5. So this is the element we're considering right now. Our small numbers are here because I is currently pointing there. Okay, so then we can say, is 5 less than 4? Okay, no swap. Okay, this gets a bit easier now. So there's no change here. Okay, the only thing that's going to happen is I'll eventually get the color right. We'll increment our J pointer. Okay, we didn't need to swap this. Okay, this belongs in the large numbers. Okay, in the 7th iteration, again, we're comparing 6 with 4, so that'll also be a no swap. Okay, so we have 2, 1, 3, 8, 7, 5, 6, and 4. A lot of space left over. Okay. So J is now pointing at 6, and again, when we're making that comparison, 6 is not less than 4, so we don't actually need to change anything. So I is still pointing here, and J will have now got to this high -1. Okay, so that position is not the last element, but the penultimate element. Okay, so this is when the for loop stops. Okay, so at this point in time, we've actually completed the most of the partition, but we still have one job left. Okay, we're ultimately trying to sort this array, and its current state is, okay, we have this, we have our small numbers here, our small pile. We have our large numbers here, but our pivot is in the wrong place. Okay, remember, we ultimately want to sort this, so this can't live here forever. Okay, so what we have to do is then take this position and swap it with the 8. Okay, so the last part of the pivot or the partition algorithm, if you remember, is swap whatever I plus 1 is plus the position of the pivot. Okay, go back over here. So our array will actually become 2, 1, 3. They all stay the same, but our pivot 4 will go there because it will have swapped with I plus 1. Remember, I at the very last part of the for loop was pointing there. So I plus 1 tells us, well, it's going to be this one. And then our 8 will get put into the final position. Okay, now it's it's accidental that 8 ended up where it should be in the sorted version of this array, and actually 4 ended up. That's just pure coincidence. You can't really take anything from that. But with that, then this completes a single partition. Okay, we've done one call of the partition algorithm. Okay, so we've swept through this once, cost of n, and we've arranged it into a small and a large pile. Okay, but the algorithm has 2 recursive branches. So once we actually have this, what we need to imagine now, the recursion will consider, maybe a different color, this as a subarray and this as a subarray, and this was our pivot, so we don't need to do anything. We know this is in the right position now. Okay, so then this is really just, we're now going to do the same thing again. We're going to call Quicksort on this smaller array. So sometimes it's called the lower array, if you like, 2, 1, and 3. Okay, and also call Quicksort on the higher array. So it's 7, 5, 6, 8. Okay, so we know we're calling Quicksort, and we have these 2 recursive branches. Now I will do exactly the same thing again. Once you do this, you will repeat the partition process. And again, this is a much smaller array. You will choose the last value as your pivot. You will initialize I to point outside this array. You will initialize J to point at the first element. And then you will do the same thing again. You will repeat the partition. You will compare 2 with the pivot. Is it less than? Yes. And then you compare I with the pivot. Is it less than? Yep. You've actually completed that. Okay. And then this will recurse again, but this time we ignore the pivot. So our array is only 2 and 1. And in this example of having the pivot as the last element, we'll compare 2 and 1. The algorithm will complete and it will swap. It will swap the order of these. So we actually end up with a sorted subarray. Okay, and then there'll be no more work to do, because when we try to divide this again, the pointers will be the same. Okay, because if you have an array of size 1, then there isn't a low and a high pointer. There's just one element. Okay, so then that's how that we recursively call that partition. It works on increasingly smaller problems until you ultimately end up with a sorted array.